Alright, so in this video we go over section 6.3, which is exponential functions. Alright, so in this section we're going to learn how to evaluate exponential functions, how do their graphs look like, and how to graph them using transformations and shiftings and all that, define the number e, that special number, and solve basic exponential functions. Alright, so let's evaluate exponential functions. Let's define them first. So an exponential function, it's a function of the form f of x equals some value c times a to the x, where a is a positive number and a cannot be 1 and c cannot be 0, sorry. And they are real numbers, any real number. The domain is going to be all the set of all real numbers. A is called the graph. A is it's called the base, which is also the growth factor. And because when we plug in 0 to that function, we get c times a to the 0. A to the 0 is 1 times c. C is usually called the initial value. Alright, so exponential function, how do they look like? Well, when we have the fact that a is a number greater than 1, well, we are going to have an increasing function like this one, 2 to the x. Okay, so to evaluate these functions, I'm going to make a quick table, a quick list. F of 0, f of 1, f of 2, f of 3. Just a few of them, not too many. And we can go with negative numbers, f of -1, f of -2, of course. Okay, let's make a quick list of this. So in this case, what are we going to get? Well, let's do the f of 0 first. So I'm going to do 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the -1, 2 to the -2. Okay, 2 to the 0 is any number to the 0 power is always 1. 2 to the first power is 2. 2 squared, which is the same as 2 times 2, which is 4. 2 cubed, which is 8. And then with negative exponents, in this case, I will write this as 1 to the second, 1/2. I mean 1 over 2, not 1 to the second. And then 1 over 2 squared, which is 1/4. And you know, when for negative values, the y value, for negative values of x, the y values are going to be very small. And for positive values of x, like 1, 2, 3, 4, 5, etc., notice how this number starts growing. Like in this case, f of 5 I'm going to do, which is 2 to the 5th power, which is 32. Huge number, right? So they start being huge. Let's look at the other case when we have a decreasing function. So this happens when a is a number greater than 0 and less than 1. For example, x to the 1/2 to the x rather. So I'm going to do again f of -2, f of -1, f of 0, f of 1, f of 2, and f of 3. That's going to be enough. That's good enough, f of 3. So I'm going to write 1/2 to the -2, which is the same as saying, well, every time we have a negative power, we can flip the fraction inside and change the exponents to positive. That's going to be 4. We do the same here, 1/2 to the -1. And in this case, we can change the sign of the exponent provided we flip the fraction. To do the first is simply 2. 1/2 to the 0 power, that's 1. 1/2 to the first power, it's going to be 1/2. 1/2 to the second power, essentially 1 squared, which is 1, and then 2 squared, which is 4. Keep in mind this property of exponents or law of exponents when you have a over b. to the m power, or n power. This is a to the n and b to the n. Basically, we distribute that power to both of them, numerator and denominator. And same here, 1/2 to the third power, that's 1 cubed, which is 1, and 2 cubed, which is 8. So in this case, we have a decreasing function. For larger values of x, we get smaller numbers, but for negative values, rather for the positives, we get smaller numbers, and for the negative values of x, we get large numbers. See the trend here, see the tendency? They are basically reversed. Okay, let's go to the next page, and let's list the properties of the exponential function f of x equals ca to the x. So the domain of this set is the set of all real numbers, or negative infinity to infinity using interval notation, and the range will be 0 to infinity. So in this case, notice one thing I didn't mention here. The x-axis is going to be a horizontal asymptote. That means it's never going to touch the x-axis unless the graph is shifted, which will be shifted, which will be in the next case. And the range, so that's for the positive case when let's see. So when c is greater than 0, we are gonna have boom 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 boom. That's the horizontal asymptote, and then the graph of the exponential. However, the case in which c is negative, remember when we have a negative, that flips the graph upside down. All right, that flips it upside down. So in that case, what we do is flip the graph or reflect it about the x-axis. All right, so that's why the range, when the initial value is negative, it's going to go from negative infinity to 0 without touching the 0. Notice the parentheses because it never touches or crosses the x-axis, unless again the graph is shifted up or down certain units. Well, in that case there is. All right, so the x-axis, as we mentioned, that's a horizontal asymptote, and f of x is 1 to 1 again. That's because if we do the horizontal line test, every single line I trace, no matter what case, no matter where I do it, it's only going to cross only once. All right, let's graph exponential functions and define the number e. So first we graph basic graph of exponential functions. Okay, so in this case, if you recall the shiftings, well, we are gonna have a vertical shift. If k is negative, we shift down, and if k is positive, we shift up. All right. So well, but what are we going to do the shifting from? First of all, I'm going to pretend that I'm only graphing f of x equals 4 to the x. And let's pretend we don't have this negative 2. So number 1, as originally, we have this horizontal asymptote at, which is the x-axis. And if I do f of, so with f of x equals 4 to the x, okay, so f of 0 equals 4 to the 0, which is 1. And then f of 1, which is 4 to the 1, which is 4. So if x equals 1, y equals 4. And then what are we going to do? I'm going to give this the shape of an exponential function passing through these points. Okay, it doesn't have to be perfect. Just be sure that this almost horizontal part of the graph doesn't touch the x-axis. It gets only asymptotically close to the x-axis. Now, notice we have 2 points to work with, the point 0, 1 and the point 1, 4. All right, this negative 2 is going to shift 2 units down. In other words, we are going to subtract k to the y coordinate. So in this case, let me close parentheses here. I'm going to subtract 2, and the new coordinates that I obtain are 0, negative 1, and 1, positive 2. So I'm going to use this blue color for this shifted function, this shifted graph. All right. So I'm going to graph 0, negative 1, and the point 1, comma, positive 2. And also in this case, it is the horizontal asymptote what gets shifted also. So also shift the horizontal asymptote, HA for short, horizontal asymptote, 2 units down. All right, so I'm going to draw a dashed line at y equals negative 2. And I'm going to do the graph of an exponential function, connecting those important points. All right, so the domain is going to be the same. It's negative infinity, positive infinity. Regardless of the shifting, the domain never changes for the exponential function. However, the range changes to, in this case, the lowest point is not going to be 0. It's going to be negative 2 to infinity. All right. And the horizontal asymptote, because it got shifted 2 units down, it's going to be the graph of y equals negative 2. And finally, we are going to have a y-intercept, which is the point where it crosses the y-axis, that is 0, negative 1. Okay? So those are the properties that we are going to list every time we do the graph of an exponential function. All right, so let's see if there's anything else we should add here. Well, I think that's about it. So that's all we need to do. All right, let's look at another example. So graph f of x equals 2 to the x minus 2 plus 3. We're going to have two shiftings, horizontal shifting and a vertical shifting. So first of all, let's pretend we don't have that negative 2 and that plus 3. So with f of x equals 2 to the x, well, we already did a few of this. F of x equals, f of 0, 2 to the 0, which is 1, and f of 1 equals 2 to the first power, which equals to 2. So 0, 1, and 1, comma 2. Okay. So those are the points, maybe 2, comma 4, why not? And 3, comma, well, we don't have enough. So horizontal asymptote with a dashed line as usual, right? And then connect the dots. And like this. Okay, so that's the exponential function without the shiftings. Now, so that means that we're going to have the points 0, 1, and 1, comma 2. So I'm going to do the horizontal shifting first. Okay, horizontal shifting. Recall that when we have, for example, a number with negative sign, it goes, we do the opposite, which is add h to the x coordinate. So in this case, h equals 2 and k equals 3. So we are going to add 2 only to the x coordinates. And because of k equals 3, we are going to add 3 to the y coordinates, giving us these new points. Okay, 2, 0 plus 2, that's a 2, and 1 plus 3 equals to 4. And for the second point, we get 1 plus 2, that's a 3, and 2 plus 3 equals a 5. So those are the 2 points that we are going to graph for the new, that should have been in blue, by the way. Okay, this blue is dying on me. Let me get another blue. Here it is. It's new. All right, so the point 2 comma 4. 2 comma 4 and 3 comma 5. Okay, so those are the points that get shifted. So in this case, well, we need to find the y-intercept. We didn't do it because f of 0 was the intercept on the previous example. So number 1, shift the horizontal asymptote HA 3 units up. So I'm going to drag this horizontal asymptote and I'm going to shift it 1, 2, 3 units up. I'm going to find the y-intercept, which is by evaluating the given function f of 0, that's 2 to the 0 minus 2 plus 3. So what are we going to get here? So 2 to the negative 2 plus 3, which is 1 over 2 to the second power plus 3, which is basically 1/4 plus 3. So in this case, while using a calculator, we get 3.25. So 3 1/4, well, it's going to be roughly here. It's going to be a little bit hard to graph, but it's going to be there. So when we do the graph, and so it passes through the y-intercept, which is 3.25. And let's state the domain. The domain, again, is negative infinity to positive infinity. The range, however, is going to be changed from the smallest y value, which is 3, all the way to infinity. And the y-intercept, we already got it. And the horizontal asymptote, we already mentioned that we shifted 3 units up. Its equation is y equals to 3. All right. Okay, let's do another example. Graph f of x equals 2 to the negative x minus 3. How do we graph now when we have some negative in the input? Well, first of all, let's pretend we don't have this. We don't have that negative 3 and we don't have that negative sign. So we're essentially graphing 2 to the x, just like the previous example, in which we have a horizontal asymptote and 0, 1, 1, 2, 2, 4, and then all we do is draw a curve connecting these points and make it look like exponential. Be sure not to touch the x-axis, only make it look like it's getting close asymptotically. Alright, so just like before, we start with the points 0, 1 and 1, 2. And then from there, we are going to do the shiftings and reflecting in this case. So start with 0, 1 and 1, 2. So in this case, we have the situation of f of negative x. we multiply the x coordinates by -1. So I'm going to multiply 0 times -1 and 1 times -1. Okay? And I'm going to get new points. So the new points that we obtain here are going to be, well, 0 times -1 is still 0. And 1 times -1 is -1. And keep the two the same. Now, because of this -3, what are we going to do? Well, going back to the shiftings, subtract k to the y coordinate. So we are going to subtract 3. And so we get 0, -3, and -1, comma, well, actually 1 minus 3, that's a -2, and this is 2 minus 3, that's a -1. All right. So let's see what are we going to do. So do we have any shifting? Well, we already did all we needed to do. So let's plot these points. 0, -2, and -1, comma, -1. Okay? And in this case, are we going to have... Alright, so we graph these points. Okay, give me a second. 0, -2, and -1, -1. So we are supposed to get, it's actually shifted 3 units down. Let me verify with my graph something it's not going on here. Oh no, that is correct. Never mind. That is correct. So, and let me delete something here. So in this case, the next thing we need to do is shift the horizontal asymptote, HA for short, 3 units down. That is, I'm going to drag this dashed line, boom, 1, 2, 3 units down. So, and what are we going to get? We are going to get a graph like this. Just representative, right? So what is the y-intercept? The y-intercept in this case is, we got it from, which is the point in which x equals 0, y whatever value is, which in this case 0, -2. The domain, again, that never changes. -infinity, +infinity, and the range, that's going to go from -3 all the way to infinity. Again, without touching, because we doesn't touch where the location where the horizontal asymptote is. Finally, the equation of the horizontal asymptote, well, we drag it 3 units down. So it's going to be y equals to -3. And let's do a couple of examples and we move on to the equations. Alright, so graph f of x equals -3 to the x minus 2. So now this is this negative sign in the coefficient of the exponential term is going to change the whole game here. First of all, let's pretend we don't have that negative, we don't have that -2. So we're essentially graphing f of x equals 3 to the x, in which f of 0 equals 3 to the 0, which equals 1, and f of 1 equals 3 to the first power, which equals 3. So we're essentially graphing the point 0, 1 and the point 1, 3. And horizontal asymptote again is the x-axis by definition of the basic exponential function. And then from here, let's connect the dots using the marker here, using the pen, and that's how it looked like. All right, so now let's see what is this negative going to do. All right, so first of all, I'm going to start with the 2 points, which is 0 and 1. All right, and 1 comma 3. So first of all, I'm going to do the shifting, the vertical shifting, which in this case is to subtract 2 to obtain new points, which are 0 comma negative 1 and 1 comma 1. All right, and then this negative is going to change the sign of the y values, that is multiply this by negative 1 multiply by negative 1 to get 0. Negative times a negative is positive 1, and then 1 times negative 1. Also, we need to shift the horizontal asymptote, what is it, 2 units down. All right, so that's the first thing I will do. I will drag this line, this dashed line 2 units down. And I'm going to plot these 2 points, 0, negative 1. Actually, yes, 0, negative 1, and 1, negative 1. However, this is not there's something weird going on here. So 0, 1, and 1, 0, 1, 1, negative 1. I think I should have shifted the other way around. Let me double check my insert a negative and delete. Okay, negative 3 to the x minus 2. That is correct. So the points that get shifted from there, second table, when 0 I get negative 3. We need to be very careful. Yes, I should have done the shifting the other way around. So let's erase this. So I'm gonna start over here because otherwise I'm not gonna get the right. So that's one of the mistakes that you don't want to do when doing graphing reflections and shifting. So in this case, we're going to do the reflection first, and then the shifting down. So reflection by multiplying by negative 1 first, and I'm going to get 0, 0, negative 1, 1, negative 2, negative 3 rather, and then I'm going to subtract 2 to each of the y components, the y values, to get 0, negative 3, and 1, negative 5. That's going to make more sense with the graph because it has to go below the horizontal asymptote. Otherwise, it's not going to get the correct answer. So 0, negative 3, that's actually the y-intercept, and 1 comma negative 5. And in this case, notice the shape of the graph. And this is going to be a game changer when finding the domain. So what do we have? We need to state the y-intercept, which is precisely this point, 0, -3, and then the domain never changes, and the range, which in this case is going to come from -infinity, and it's going to stop at y equals -2. Okay. Now, one last piece of information: the horizontal asymptote HA, it's shifted down to units, y equals -2. Okay. Now let's introduce this e to the x function. This is a special number that has a value of 2.71, very similar to pi, which is 3.1415, blah blah blah. Well, this number e, which has a value of 2.71. All right, and it also has infinitely many repeated decimals, just like pi. So let's graph that function. Let's see. So where in the calculator can you find it? So first of all, let's go to y equals. Okay, that's so you can see the function. You are going to press second and press the ln button, so you can reach the e to the x function. Wait a minute, that's not second e to the x, and this e value is going to be there, so e to the x. All right, e to the x and graph. Well, it's going to have essentially the same form as the other exponential functions we have been doing, except that if we go look at the table, when x equals 0, well, the y-intercept is 1. When x equals 1, that's e to the first power, which is 2.7183, blah blah blah. Then e squared, and then e cubed. See how big these numbers get. So 0, 0, 1, 0, 1, and 2, which is 2.71 roughly here, and 2, 7.3 roughly here. And then the horizontal asymptote remains the same. And let's draw the graph of this. Alright, so this is all of it as far as graphing exponential functions. The last of this section is to solve very basic exponential equations. So the fact that these functions are one-to-one, that is, for example, if I have 3 to the x, for example, y equals 3 to the x. If x equals 0, I'm going to get y equals 1. If x equals 1, I'm going to get y equals 3. If x equals 2, I'm going to get 3 squared, which is 9. Notice none of the x values have the same y value. You know, like for example, parabolas. On the other hand, remember, those are not one-to-one. The origin 0, 0, but if I plug in -1 and 1, I get both +1. If I plug in 2, I get 2 squared, which is 4, and -2, which is also +4. So the y values get repeated for the same, for different x values. So in this case, we use the one-to-one-ness of an exponential function to solve equations. If we have the same base but different exponents, well, then the exponents must be equal. So we use that property to solve equations. So how do we go about solving equations? Now observe, in this case, that the x, just like in the functions, the x is the exponent. It's no longer multiplying a number or dividing a number like in rational functions or inside of a radical. No, in this case the x is in the exponent. So how to use this property to solve equations? Well, observe the bases 3 and 81. If you notice, the number 81 can be written as a power of 3. In some cases it may not be able. We're going to look at those cases in the preceding sections. However, in this case, 3 to what power gives us 81? That's 3 to the 4th power. So essentially what this theorem is telling us that we can cancel the bases and just keep the exponents u equals v, u equals v. So in this case, basically 3 and 3 cancel, and we get x plus 1 equals to 4. Subtract 1 to both sides to get x equals to 3. There are cases in which, well, we have the basis 4 and 8. Well, observe that in this case the number 8 is a multiple of 4, but it's not a perfect power of 4. So in this case, we are going to decompose both numbers. In this case, we only work with the number 81 to write it as a power of 3, because this one was already the simplest power. Now in this case, well, we are going to have 4, which is the same as 2 squared to the 2x minus 1. And at the same time, we're going to have the number 8, which can be written as 2 to the 3rd power. All right. And everything to the x plus 3. Okay, now when we have the power of another power, we multiply the powers. You might want to recall that properties of exponents. When you have a to the m to the n power, we can do a to the m times n. In other words, I'm going to multiply 2 times 2x minus 1. So 2 to the 2 times 2x minus 1, and 2 to the 3 times x plus 3. All right. Again, we got to the point in which the bases are the same. Cancel the bases and keep the exponents. All we have to do here is use the distributive property to solve this equation. So 4x minus 2 equals 3x plus 9. And this is a first degree equation, linear equation. Subtract 3x to both sides. And that's going to give us 4x minus 3x. That's a x minus 2 equals, cancel these guys right here. I get 9. And add 2 to both sides to get x equals 11. So we're going to get more in depth with this type of equations in which we won't be able to express the bases as powers of the same number, of the same base. So, well, in that case, we're going to combine logarithmic and exponential properties. But that's going to come next on the next sections. Typical questions. For example, you're given a statement here, 6 to the x equals 2. What is the value of 6 to the negative 4x? All right, so our job here is we need to convert this 6x into 6 to the negative 4x. Okay, so first, how is this 6x different from this 6 to the negative 4x? Number 1, there is a negative sign. And number 2, there is a number 4 in there. So first, I'm going to raise both sides to the 4th power. All right. That's going to give us, again, using the same property that I listed above right here, power of another power, multiply the powers. So 4 times x, that's going to be 6 to the 4x, not times. Make sure this quantity looks like a power, not like it's multiplying. Okay, let me make this 6 a little bit bigger. So the 4x actually looks like a power. And then 2 to the 4 power, that's a 16. There's one more thing missing here, which is raising both sides to the -1. And by the same property, 4x times -1, I get 6x. 6 to the -4x. And 16 to the -1 is the same as 116. So the value of 6 to the -4 is 1/16. Another example like this, well, we are given a to the -4x equals to 64. What is the value a to the x? So now we have a bunch of garbage here, like x a to the, actually, I need to fix this. It has to be instead of, otherwise it's not going to work out. A to the -3x, not -4x. It will be updated in a handout. So I need to get rid of this -3 to get x by itself. So first of all, the first thing I do here is to raise to the -1 on both sides of this mini equation in order to make this positive. That's going to give me 1/64. All right. Then I'm going to use this property backwards so you can see it better. I'm going to go from here to there, and I'm going to take out one of the factors here. I'm going to take the 3 outside. When you use this property, you can also say that a to the n over m. So if this is your starting point, a to the mn, you can have the m inside or the n inside, the m inside and the n outside, or the n inside or in the m outside. Now, I'm going to do, in this case, I'm going to take the 3 outside. I'm going to have, so a to the x to the 3rd power, that's 1/64. Now, the question is, how do I get rid of this cubed? Well, by doing the inverse of cubing, which is taking the cube root. All right. And then, in this case, this cube root will cancel this cube power. And we are going to be left with a to the x. Now, what is the right-hand side reducing to? Well, the cube root, don't forget the index, cube, that's 1/4. Because 1/4 cubed is going to give us 64. So 1/4 is the final answer. And this is a good place to quit. I will see you in the next video.